So today we start with a new chapter. It's about second order processes. This class of stochastic processes is very important for signal processing and communication engineering. Okay. So first of all, I would like to talk about the space. So what is this space? Well, you know, this is a probability space, right? We have a sample space omega, we have sigma algebra, and we have the mean matrix. Okay? And the L2. So what do we mean L2? So L2 is the set of all complex value, random variables. It is a set of complex value, random variables on the probability space with the second moment. Okay? Just this is very simple with the second moment. Okay? Alright. So now the first result is about the Stochastic inequality for random variables. We know Stochastic inequalities in linear algebra, okay, in inner product space is that the same. It appears in many different contexts. So for stochastic process, especially for probability theory, if two random variables, right, have second moment, okay, and of course here the difference here is that I put a tilde, okay. So there's some difference between L with tilde and L without tilde. Right. So first of all, L tilde is a set of all complex values random variables. So in L tilde, and if x and y are in this vector space, so that means that each of them has finite second moment. Right? So it has finite second moment. That's why this is finite. So we can take the square root here and square root here. And so the meaning is that the expectation of the s value of the product of two random values x and y is less than or equal to the square root of the x value, the square of the x value of x, and the square root of the expectation of the square of x value of y. Anyway, so as we know, so expectation is finite, as we know. We can only use expectation of finite. Okay? Because the square of a random value is also a random variable. Okay? So you think x squared as a single random variable, right? So the expectation of x squared is finite if and only if the absolute value of x squared has finite expectation. Therefore, this is we know that from chapter 1. Okay. So now, so let A to be this quantity, B is this quantity. Okay, and we know the geometric average of two non-negative random variable is no more than the arithmetic average, right? So this is the basic Cauchy inequality, right? So this is called the Cauchy inequality we learned in the middle high school. Okay. Right. So this is true for all the omega, because for each omega it's just a complex number, right? Because x and y are complex value random variable. So given a sample omega, then it's a complex number. So this is just numbers here. And now if we check the expectation, so when we check the expectation, we have here. Okay, so we have here. And we complete the proof. Okay, and so well, Because you see, this is square, right? When you take the square root, then you just happen, this is the product of x value of x and x value of y. So now we have this one, right? And we know that this is 1 here, because this is 1, 1 plus 1 is 2, 2 divided by 2 is 1. So you move AB to here. Okay? So you move AB here, then you complete the proof. It just is a very simple proof, you can see. Complex value, it means that because we know a random value is a function from the sum space to the set of all complex numbers. So it's called the complex value random variable. Because if it's go to R, then it's called real value random variable. So that is the differences here. But we know a random variable is more than a function from omega to c. It should be measurable, right? So for every Fourier set, for real value random variable, for every Fourier set in R, the inverse mapping must be an event. Similarly, you can think about C as, because the geometry is just a plane, right? A real plane. Okay, so a Fourier set in C is the same as a Fourier set in R squared. Okay, just like and for example, in the complex plane, a rectangle here. So this is the real part. This is the imaginary part. So here, so this region is a Fourier set. Okay, and the inverse mapping for a Fourier set in C should be an event in F. Okay. Right. So that I think complex value, the random value is just pretty much like a real value random value. Just like x has real part and imaginary part. So we may think about it as it's just a random vector. Okay, so don't forget A is this quantity, B is this quantity. Right. So the A square is equal to the second moment of the x value, the square of the x value of the x, and the B square is equal to here, is equal to the expectation of the square of x value of y. Please put a red parenthesis here. Okay. Okay, so Schwarz inequality, we have that. Okay, so now we can show L2 space is a vector space over C. Okay. By the triangle inequality for complex numbers, so this is a triangle inequality, right? For any complex numbers, we have this triangle inequality. And then by taking the expectation, okay, so now we can take the expectation here of this one. So this is the square. So it's the second moment of the x value of x plus y. Okay, and we find that this is the upper bound like this one, but this expectation of the x value of the product of x and y is finite by the Schwarz inequality, right? So the three terms are finite, and so their sum is finite. So that's why this is finite. So this proves that x plus y is also in L2 too. Okay, so it's closed under vector addition, means the addition of random variables. And also, for any complex number alpha here, we have this quantity. So of course, this is also finite. So this set is curves under scalar multiplication. Right? So with these two, we know that the L tilde space is also it is indeed a vector space. Okay, now we define an inner product in the space. Okay, so now we define an inner product. So the inner product between two random variables, because now in the L2 tilde space is a vector space. Okay, and now we define inner product between two vectors x and y. And the definition is here is the expectation of x times the complex conjugate of y. This is complex conjugate, right? So so this is, and we can show that this definition satisfies the three axioms of inner product. The first one is non-negative. Okay, so for any random variable x and y, okay, the inner product of x with itself must be greater than or equal to 0. Okay. The second one is Hermitian symmetry, that if you change the order of x and y, then you have to change, it comes to the complex conjugate. The third one is that for the first argument x, it is linear. Okay, this is by linearity of the expectation, so it's linear. The only thing is that if random variable x is 0, of course this inner product is 0. But the problem is that if the inner product of x with itself is 0, then x may not be equal to 0. Okay, may not be equal to 0. So that it's not a real. So the first axiom is not perfectly satisfied. But we know that if we know that the second moment is 0 if and only if x is 0 with probability 1. Okay, with probability 1. X equal to 0 if not means that x is identical to 0. Not. Okay, so it is possible x for some x omega. So it's just an event. The probability of x equal to 0 is 0 only. Okay? But the set, this event may not be empty. Okay? May not be empty. But even though this event is not the empty event, the probability is still 0. Okay? Then we say that x is equal to 0 with probability 1. Okay? So now the proof here is here. Okay? I give you a simple proof. Why? But this is true. Yeah.
Otherwise, may not imply that x equals 0.
Oh, yeah, because we have examples to show to you. That
Neutralizing in the picture.
No. All right. First of all, this is true that this is 0, right? If and only if x is equal to 0 with probability 1. But this is just with probability 1. Which will not mean that x is equal to 0 identically. That is different. That is different. But for example, you may for example you can define x omega. For example, you can divide. You can E1, E2, E4. Alright? So the can be C1 up to omega. Okay, so the size due to the first part is 16. Right? For example, we can partition some space into 4 pieces. Okay, and we form a second algebra. This second algebra gives us this one. And then we define a probability measure. Alright, but probability E4 is 0. I can define that. Okay, now I define a random variable from to R such that x omega is equal to 1, 2, 3, 4. If omega is in E1, omega is in E2, omega is in E3, omega is in E4. Okay? So now I have a random variable now. Okay, but then okay. Okay, sorry. X is 0 if omega not in E4 and the 4 and 1. Maybe I just sorry. Okay, so I define a random variable which is 0, 1 value. And the value of the random variable is equal to 0 if omega is in E1, E2, and E3. But x omega is equal to 1 if omega is in E4. Then x not equal to 0, right? It's obvious. Because for all the omega in E4, the value is 1. 1 is not equal to 0. But x is equal to 0 is probability 1. Why? Because the probability that x not is equal to 0 is that probability that x is in the E1, E2, and this is 1. Okay? This is 1. Because the event x equal to 0 means that the omega is in E1, E2, and E3. So this is the probability of the union of these three events. E1, E2, and E3, and is equal to 1. Because 1/3 plus 1/3 plus 1/3 is 4. Okay. So x is equal to 0 is very well, but x is not identical to 0. Okay, so now, but I have to prove that this is true if if x equals to 0 equals to 1. Alright, so consider this direction, that the expectation of the square of the f value of x equal to z. So now, for each epsilon greater than 0, okay, for epsilon greater than 0, that this expectation is greater than equal to this expectation, because that it is the 0, 1 function. Okay? And we just give on here. So for all the x greater than equal to epsilon, the value is 1. But if x, the value of x is less than epsilon, then the value is 0. Okay. So the lower bound is that the e square and this one. Okay. The expectation right? What is this? Is that x sum x square, right? So it's this integral. So the expectation actually is this integral. Okay, and the x is in this range. Right. Okay, and here we have a lower bound because that we integrate over all the x greater than equal to epsilon. So the lower bound is that x greater than epsilon, and this is epsilon squared. Okay. And this is epsilon squared, and the probability that x greater than equal to epsilon. Okay, so it's here. Right. So 0 is greater than equal to this one. Okay? That implies that this is 0. Implies this is 0 for every epsilon. Okay? Now the event x not equal to 0 is the union of those events. Because if x not equal to 0, then x should be greater than some small numbers. Okay? So that this event is the same as this union. Okay? But it's not a disjoint union, okay? Not a disjoint union. This event may have intersections, non-zero intersections, but it is the union of this one. So the probability, right, would be by the union bound. We know the bound. We know that the probability of this union will be less than or equal to the sum of the probability of each event here. Okay, but each event is 0, right? We just proved that. So even you have remaining 0 to some degree, it's still 0. Alright, so this probability is equal to 0. Alright, so we say that x is equal to 0 with probability what? Okay, so I show you directly. So I have shown that if this is true, then x equal to 0 is probability 1. Okay. Conversely, if we have a random variable which is equal to 0 with probability 1, okay, then we must have this one. Okay. Now, so the ambiguity between a random variable with this is 0 and the 0 random variable is that x is equal to 0 with probability 1. So in the second order process, I mean, in these discussions, we will identify that a random variable which is equal to 0 with probability 1 to be represented by the 0 random variable. Because in distribution, the distribution of x is the same as the distribution of the 0 random variable. Because all the probability are concentrated on the 0. Okay, so these two random variables, x and 0, has the same distribution. Okay, so they are equivalent random variables. Okay, then they are equivalent random variables. So in this sense, so the two random variables are said to be equivalent, denoted as here. If x and y is probability 1. Okay, that means that x and y has the same probability distribution. And you can see that x and x is equivalent to each other. So it has reflexive property. So x is equivalent to itself. And if x is equivalent to y, then y is equivalent to x, of course. Right? And if x is equivalent to y, y is equivalent to z, then x is equivalent to z for the transitivity. Okay? So if x and y has the same distribution, and y and z has the same distribution, then of course x and z have the same distribution. So that's trivial. Okay, so we established the equivalent relation among the random variables in this, tilde square space. Right. And we will denote such an equivalent class with random variable x belongs to as the bracket of x here. And we call x as a representative of the class. Okay. So now the L squared without the tilde will be the set of all equivalent classes. Okay. So now each vectors in L2 is actually an equivalent class. It represents a class of random variables. They have the same distribution. Okay? They have the same distribution. So we allow this ambiguity. It's very important because that in practice, if we want to observe two random variables, and if these two random variables have the same probability distribution, then we cannot distinguish them. We can't. Because all the observations, they're all the same behavior. Okay? So we cannot. So in practical point of view, especially in signal processing or in engineering, that we for sure we can identify two random variables with the same distribution as the same. Okay, so now we will consider the relative space, and in many situations we will not use the bracket form. Just take one of the representative of the class X. Right. So in the context we usually meet the bracket, the square bracket here. But in theory, if you want to have a careful discussion, then it is recommended that to use the bracket notation to indicate that this is indeed an equivalent class of random variables. Okay, so that actually the addition of two classes actually is the class corresponding to the sum of the two representatives. This is the same. And similarly, the scale times a class is corresponding to a class, all right, of the alpha multiplied with the representative x. So they have the natural correspondence. Okay? And it is well defined. I think you can check. Because I give you a rigorous proof that indeed this is true. Okay? But I think it is not just for you to check it. Furthermore, an inner product can be defined. So an inner product of two equivalent class is actually can be defined to be the inner product of their respective representative. You can take any representative from this kind. You can take any representative from this kind and to make the inner product here. And they will have the same value. Okay? So they will have the same value. Right. And so with the equivalent class, we know that the equivalent class has the inner product 0 with itself. If and only if the equivalent class is corresponding to the 0, the class having the 0 on the value. Okay? Alright. So now the L2 space without tilde is a really indeed a complex inner product space. Okay? It's inner product space. Hereafter, we will identify an equivalent class in L2 with any of its representative random value. Okay? That I think you can. It is very clear. You will not cause any ambiguity, right, in the context. So in particular, we will say that x equals to 0 in L2 squared to mean that the x is in the same class with the 0. Okay. So now we have inner product space, so we can apply the result in linear algebra to the study of second order process. So now the inner product is non-negative, so we can define a norm called the actual norm of the random variable here. So the norm square, the square of the norm is just the inner product of the x itself. Just like the Euclidean norm we studied in linear algebra. Okay? And so the triangle inequality, now we can state that. Right? We can state. Yeah? We just proved that already. So actually we have this inequality, this triangle inequality. So the length of the sum of two vectors is less than equal to the sum of the length of the respective vectors. Okay? So this is the triangle inequality we have. And the norm here, with the norm, then the norm can be served as a metric. Alright? So that, for example, the difference of the norm. So because we use the norm to define as a length. And so this is the distance. Okay, so this is the distance between two random variables. So of course, the distance between two random variables should be non-negative, of course. And the distance is 0 even only if x and y are equal. When we say x and y are equal, means that they are in the same equivalent class. Means that they have the same distribution. Okay, so two random variables has the same distribution. Then their distance is 0. Of course, there is no distinction between them from the observations. So we can say that the distance is 0 if and only if x and y have the same probability distribution. Okay, so actually they are equal with probability 1. And also we know the distance between x and y is the same distance with y and x. So we have symmetry. And we have the triangle inequality, of course, right? The x minus 1 is less than equal to x minus z minus 1. Okay, so it's a distance. Okay. So now we may regard the quantity as the distance between two random variables. Okay, so the distance between two random variables actually is the norm of the difference of x and y. Okay, just like in the Euclidean space, we can know the distance between two vectors. The distance between two vectors is the norm, is the length of their difference vectors. Okay, so for example, we have the two vectors here, E and W. Yeah. So the distance between two vectors is here. So this is W minus V. Right? So this vector is, and then the length. This is the distance between W and V. Okay. So this is the geometry of the second order, the L2 space. Okay. All right. So we have the length, we have distance. So now we have geometry. Okay, just like in the Euclidean space. So now we have the geometry in the inner class space of all non variables with finite second moment. Now we have geometry, right? So we can apply the calculus. We can do the calculus. A sequence of random variables, right, in the complex inner class space is said to converge. Okay, we say that a sequence of random variables converge to a random variable in each space. If there exists a random variable x in the L2 space such that the distance between xn and x go to 0 as n go to infinity. Okay? So the concept is the same as the concept we studied in the vector calculus. Because in the n-dimensional Euclidean space, a sequence of n-dimensional vectors converge if there is an n-dimensional vector such that any vector in the sequence is distance from the limiting vector goes to 0. Okay? As n goes to infinity. So that xn a sequence of vectors in Rn or in Cn, right? So Cn. So each xn is n-dimensional complex vector. And we say that xn goes to x, right? As n goes to infinity, if and only if the distance goes to 0, as n goes to infinity. Right? So this is the definition. A sequence of vectors in Cn converge to x. Okay? If and only if the distance, okay, between xn and x goes to 0, as n goes to infinity. So the distance gives us the neighborhood, right? Because in calculus we need the distance property. All right, so we consider a sequence of random variable converge. This concept, so convergence of sequence of random variable is well defined in L2 space. Okay, in L2 space, because L2 space is an inner product space. Okay? And it can be shown that X is unique. Of course, this is the same as in calculus, so I don't need to repeat it again because you learn a lot in calculus. Even though maybe you will learn the calculus for C1 or R1 n-dimensional in the real life, but it can be extended to n-dimensional space without any difficulty. So that it can be shown X is unique, and we call X as the limit of the convergence sequence X. Okay, so a sequence of random variable converge to a random variable, okay? By using the distance nature. Okay, so what is this the distance measure? For random variable, we say that xn minus x go to 0. That means that the inner product xn minus x, xn minus x goes to 0. Okay, as n goes to infinity, as n goes to infinity. So what does that mean? This means that expectation of xn minus x, xn minus x comes conjugate. So this expectation goes to 0 as n goes to infinity. Okay? This is the inner product before. So that means that a sequence of random value xn converge to a random value x if and only if this expectation, the expectation is that the difference times with its complex conjugate, and we take the expectation, goes to 0. Okay, so every time you can use this original definition of inner product to do it, but it is more convenient to use the notation for linear algebra because it's called so universal, right? So you just use the norm. But don't forget how to compute the norm of a random variable. So now we can define a concept called Cauchy sequence. So what is a Cauchy sequence? So we say a sequence in L2 space is a Cauchy sequence. If you take Mn and as big as enough, so that the xm minus xm, the distance between two random variable in the sequence goes to 0 as Mn approaches to 0 simultaneously. Okay? And in the epsilon data, notation said for every epsilon, right, you want the difference to be the distance between two random variables, right, less than the epsilon, to allow the error here. Then we can find an integer such that for any nm greater than this number, right? So nm greater than this number, then the difference, then the distance between these two random variables will be less than epsilon. Oh. So it's clear that every convergent sequence in L2 is a Cauchy sequence, of course. If it is convergent, if it satisfies condition, then it is a Cauchy sequence, of course. This is the same as we have in calculus. Now, but the converse may not be true. A Cauchy sequence may not be convergent. But in calculus, we say in Cn or in Rn, any Cauchy sequence converges. Why? Because the set of all real numbers is perfect. We have a completeness axiom. Because that for real numbers, we have 10 axioms that we cannot prove. Okay? And the 10th axiom is that any bounded set of real number is this upper bound. This is called the supreme axiom of the set of real numbers. And it's an axiom because we cannot prove it. Okay? We cannot prove any bounded set of real number is this upper bound. Okay, so this is, and with that we can prove any Cauchy sequence in Cn is a convergent sequence. So that we can solve the convergent problem that we can show if a sequence is a Cauchy sequence, just show it is a Cauchy sequence. Then we say that there exists a limit, even though we don't know it, right? But we can be sure that the sequence should converge to a vector in Cn if the sequence is Cauchy sequence. A Cauchy sequence means here, right? Means here. Okay, but in general, in L2 space, that may not be have this property. Okay? So we give a name. If every Cauchy sequence in L2 converges in L2, then we call this complex inner process to be complete. So now Rn is a complete inner process. And we use this fact in calculus, even in advanced calculus, a lot. This is the basic property we have for the n-dimensional Euclidean space. Because every Cauchy sequence in this inner product space converge. Okay? So it's complete. And so in mathematics, a complete complex inner product space is called a Hilbert space. Okay. Hilbert is a great mathematician in the history. And so we name this space to be a Hilbert space. Okay? It's a very important space in analysis. And also very important for the engineering discipline. Even finance, a lot of mathematical branches. Right? So that complete complex inner product is a Hilbert space. So Cn is a Hilbert space. Okay? So Cn is a Hilbert space we have. All right. So fortunately, very fortunately, okay, the L2 space is a Hilbert space. Okay, and so so we are very lucky for this space to be Hilbert space. And once we prove this property, then a lot of property we can obtain immediately. Just like we have many properties in Cn. Okay, Cn. All right. So here is so I give you the idea of the proof. Suppose the action is a Cauchy sequence in the L2 space. Okay. So of course that there exists a subsequence in 1 and 2 such that the difference is less than 2 to the minus I. This is possible because that in here, for a Cauchy sequence, we can preset an adder, right? For example, we can preset epsilon to be 2 to the minus I. Because for I bigger, then 2 to the minus I is very small because it is potentially decay, right? But even though we can always find a number such that if n and m is bigger than this number, we have the distance between xn and xm less than this epsilon. So we can construct one by one, right? First, we can select n1 and then n2, etc. So with these subsequences, that we have the distance, they are decay exponentially. Okay, so in particular, we have this construction, right? So xn sub I plus 1 minus x of n I has distance less than 2 to the minus I. 2 to the minus I is very small. Okay, if I is big, very small because it decays exponentially. So we define a random variable, okay, yk, to be the sum of the difference between the successive random variable. Okay, so of course yk is a random variable. And it's clear that yk is a monotone increasing sequence of non-negative random variable. So it becomes bigger and bigger because the summand is non-negative because we take the f value. So that yk increasing, okay? Alright, so it converges onwise. Alright, it converges to that. Okay. So we can define a random variable y, which is the sum of these random variables. And then we can apply the back monotone convergence theorem. Okay. It says that if we have a sequence of monotone increasing random variables, then the limit, because what is the limit of yk? Okay. So the expectation of the square of y, this is the limit of y. We can exchange the expectation and the limiting process. Okay, so this is the basic idea of the back monotone convergence theorem. And so we have this one. Okay. So now by the triangular inequality, the norm of yk, so this is actually the square of the norm of yk. So yk is always non-negative. So the norm of yk by triangular inequality, we have it is less than 1. So for all k, that it has an upper bound, common upper bound, which is equal to 1. Right? So which implies that this is the expectation is less than 1. Alright, so we prove that y is in the L2 space. Okay, because it has the finite second moment. So now the constructed y is in the L2 space. And of course that the random value of x is finite, this will be 1, of course, because it has a finite second moment. So it has, and so the series converges absolutely. This will be 1. Okay, so it must converge because this is finite. So it converges absolutely. This will be 1. Okay. So we let x to be the limit of the series. This is the limit. Okay, so when the series converges absolutely, but if because we just say that it's converged absolutely with very y, right? So if it does not converge, then we just say that the random variable x to be 0. That's fine. Okay. And then for the partial sequence, you can see for the partial sequence here that this is just what? Just equal to a random value in the original sequence. So it says that the sequence x and I, the sample sequence, converges pointwise to the random variable x. So we explicitly find a random variable x such that this sequence of random value converge to it pointwise. Okay, with square b1. So it's very strong. Okay. So we next show that the limit of the Cauchy sequence converge to x in the electron norm means that in distance that xn minus x equal to 0. But it's easy because that because the x already they are Cauchy sequence. Even though the x is the limit of a sample of a subsequence, because this is the subsequence of the original Cauchy sequence. Okay, and this is subsequence converge to x, as we know that. So we can show you that because that xm, the Sn sequence is Cauchy sequence, so we can set epsilon for all. So we can first we select an epsilon, and then we can find capital N. So when Nm is greater than equal to capital N, the distance between Xn and Xm is very small, it's less than epsilon. In particular, the xi for some I, xni, okay, minus xm is less than epsilon. Alright, and so the x minus xm is the limit of the sequence. So the sequence. So that by a lemma, so I quote the lemma here. Right? Quote the lemma here. So the lemma just that this is the limit, right? So that is the lim of the sequence. And the lim, the expectation of the lim of a sequence is less than or equal to the lim of the expectation. It's called the Bethel's lemma. Okay? But it is applied to the lim, not applied to the limit. Okay. So we have this inequality, and the expectation, we know that it's an upper bound epsilon, right? Yeah. So that the upper bound is epsilon square. Well, so okay, so actually the distance between x and xm is smaller and smaller if we can take epsilon smaller and smaller. So that we just show axis in L2, of course. I think this is a repeated part from the previous one. But anyway, but you can this is show to you again that x is also in L2. So that x is in L2, and we know the distance between x and xm is as small as possible. So xm, the original sequence converges to x. Of course. And so that we prove that for any Cauchy sequence, we can find a random variable x in L2 such that the Cauchy sequence converges to x. And so the complex inner product space L2 is a Hilbert space. So this is the proof to show that this complex inner product space is Hilbert space. So Hilbert space in geometry is pretty much like the CN, the n-dimensional Euclidean space. Okay, so it will be as easy as we do something on n and CN to do with the inner product space of all random variables with finite sigma moment. Okay, so we have so this is very basic, all right. And so we can do the calculus, the differentiation, and we can do the integration, as we did in the Rn, in the Cn there. Because in Cn or in R, we do the multi-dimensional differentiation. For example, partial derivatives, a lot of things. So that this is the basic thing. And so if we now up to this point, we are able to prove that the space is a Hilbert space. Okay, so let's take 5 minutes break. Okay. So the picture is like here. This is L2 space. Okay. And we find over density. The density is a set of random variables. Okay. And so for any random variable in the space, so for any random variables in the space, say here, x here, then we can find a sequence. So this is x1, x2, x3, probably no point here. And here, x4, right? So that xn goes to x, right? In L2 norm. That means that xn minus x, so the distance between x and x goes to 0, and n goes to 3. And the point is that xn are in the W for all n. Okay? So W, so we say W is a dense set of the space. If for any random variable x in the space, we can always find the sequence xn in the W, and this sequence will converge to x in the L2 norm. So it's called dense. So that's the idea, right? That we have geometrical meaning. And now we will find a spatial density. For example, discrete random variable with finite many complex values are called complex simple random variable. So complex simple random variable are random variables which has finite many complex values only. Okay. So now the following theorem provides a dense subset of the Hilbert space L2 space. So what is this one? The set of all complex simple random variables is a dense subset of the two. Okay, maybe I'll give you an explicit formula. Okay, so a complex simple I'll give you, what do we mean a complex simple random variable? A complex simple random variable x is a random variable such that x equal to That's that. There exists C1 equal up to CK, C, and C1 equal up to DK, DF with detailed union. So that U1, U2 up to EK, they are disjoint, and the union is omega. And this is Ci for all. Okay. So a complex random variable x is called a complex simple if x is omega equals Ci for all omega in the EI. Okay. So the point is that the sum space can be partitioned into k parts. Okay, and in each part, the random value has value, a constant value Ci. So it's called the complex simple random variables. And the set of all complex simple random values is a dense subset. Because complex simple random is so simple. So it's very, very simple. But it is a dense set. It satisfies this property here. Of course, every complex simple random variable has second moment, of course. It must have second moment because it has only a finite number of values here. So it has second moment. And so X is a subset in L2, of course. Right. And the rest of the proof, I think I just omitted because that I give you a very detailed proof to show that such a set of all complex simple random value is dense. Just to show that for any random value X in L2, we can construct a sequence of complex simple random variable, and this sequence will converge to X in L2 mode. Okay? So I think I just omit the proof. Okay. Alright, so now we are going to the differential calculus of on the L2 space. Now, a second order process. Now, I formally define what do we mean a second order process. A second order process is a mapping xt from a set T of the real line. So we use T as time parameters. Okay, from a subset of the real line into the Hilbert space. Okay, so you can think about T as in just like a function from an interval, for example, a function to a vector function, yeah, from like AB equals to Cn. Okay. So it's a function, right? So for each t goes to f of t is a vector. So f of t is a vector. So it's a vector value function. Okay. A second order process can be think about as a function from the subset of the time parameters into the Hilbert space, into random variables. So that the x itself, so now x goes to L2. Okay, so the L2 is just like a Cn, as we know. It's a Hilbert space. And the T is just a subset, just like an interval. So So most of the time the t is an interval. Okay, t is an interval. So you can think about a second order process is a curve in the Hilbert space, just like a vector value function is a curve in Rn. Okay? For example, if a curve from AB to R2, okay, for example, an R2 in a plane, so you can see that this is, okay, go to here, and this is FA, this is FB, and here this is FT. Okay, so look, this is the from the origin, right? Because each one is a vector. So you can track to a curve. So it's a curve, right? A function here is a curve. But to be a curve, the function should be smooth enough. Right? Should be smooth enough. So we talk about a lot of geometry for the curve in the Euclidean spaces. So a second order process is a curve. So now a stochastic process, when the parameter can be interpreted as the time parameter, then it's just like a dynamics, right? Or a curve in the Hilbert space, L2 space. Okay, just like a curve in a complex Euclidean space. So this is picture, right? We have a curve. Just like here. So a random process, a second order random process, just like a curve in a L2 space. So we can have here. So it's probably here. Okay, so it's a curve. So it is XA. Here is XB, and here is XB. And so each one is a random variable. So XA is a random variable in L2, XD is a random variable, and XB is a random variable. So as t goes on from A to B, then the random variable move in the L2 space this way. Alright, so this stochastic process now is a curve in the L2 space. And in this section, in L2, we will assume T is an interval. For example, T is the whole real line, or T is just this semi-infinite ray, or T is just an interval, just like SA, SB. Anyway, it's just an interval. Okay, just an interval. Any questions? Okay, so now we will deal with second order process, right? As a curve, all right. And so we use the calculus, so we cannot define differential calculus. So a second order process over the time interval, a set of time is said to be differentiable at an interior point of t. Okay. So it's an interior point. It's not on the boundary here. So A is not interior point. B is not interior point. Any point between A and B is an interior point. Okay. Just like here, 0 is not an interior point. It's a boundary point. So we said a second order process is said to be differentiable at an interior point if that t0 plus h minus xt0 divided by h. So this is a random variable. Right? The difference between two random variables is a random variable divided by h is also a random variable. And because L2 is a vector space, so this random variable is also in L2. Right? Because it's a linear combination of this random variable and this random variable. But we know it's a second order process, so this random variable is finite second moment. This random variable also is finite second moment. Right? So this random variable is also has finite. That this random variable also has finite second moment. So it's in L2. And now we have a sequence, right? As h changes. Now, as h goes to 0, this sequence has a limit in L2 norm. And we call this limit as S prime. Okay. So S prime is the derivative of x of t at t equal to t0. Okay. Okay, so the reason why we can define the derivative is because that we have geometry in the L2 space. Here, this means that for any sequence Hn in R, such that Hn not equal to 0, because H cannot be 0, otherwise it is undefined. But Hn will go to 0 as n goes to infinity. Okay? And we also ask the T0 plus Hn is in T time parameters. That's fine, because that T0 is an interior point. So if Hn is small enough, then it will be in the interval, in the set T. And so Xn, the derivative here actually is the limit of the sequences with the time parameter Hn here. And the selection of the sequence Hn, right, doesn't matter because the limit will be the same. So this is the meaning of this definition. This is just like the derivative we studied in calculus. Okay. So this is the system idea. Okay, so now we can talk about the continuity. So we say that a second order process xt is continuous at point t0 if that the Tn, xtn is limited to xt0 in L2 norm for any sequence Tn such that Tn goes to 0. You have many different sequences to approach to C0, but the corresponding limit will be the same. This is the meaning of continuity. Okay? This is the meaning of continuity. And as in calculus, if x of t is differentiable at an interior point of t0, then x of t is continuous at t0. So differentiability implies continuity. This is a well-known result in calculus. And so this is the same in the L2 space. Okay? So if the curve here, so if this curve is differentiable at each interior point t, then the curve should be continuous. So it's a continuous curve, right, in the L2 space. Any questions? Now we define covariance function of the second order process of t. Here is a covariance function here. The covariance function actually give us the inner product between random values in the curve, right? So it's the inner product of x of x and x of t. So this is the inner product. So we define the covariance function as the inner product here. So the covariance function record geometric properties of the second order process because it gives us all the inner product before. Right. The geometry of a curve, as we know, comes from the inner product. So the covariance function is very important in the study of second order process because it records this inner product. Okay? And of course, the covariance function is a complex value function on the Cartesian product of t and t. So we will show that the properties of second-order process is closely related to the property of its covariance function, as you can see from here. All right, because all the geometry of the curve xt depends on the inner product of the vectors in the curve. Right. So before that, we prove a lemma, which is a fact in linear algebra, because it is true for any inner product space. So suppose we have an inner product space. Here, H is a complete inner product, not necessarily Hilbert space, just a common complex inner product space. Suppose that we have a sequence of vectors converge to x, another sequence of vector yn converge to y. So we have two sequences. Then the inner product ym and mn, right? The inner product of x and y. When we take the limit as mn goes to infinity, then it will converge to xy. Okay? Converge to xy here. So that means that because x is the limit of xn, y is the limit of yn, and so the inner product is commutable with the limit. So you can move the limit out of the inner product without changing the result. So this is called the continuity of inner product. Okay? The inner product is continuous. So we can apply this result. This is true for any inner product space. Right? So I omit proof, and we will use this property for inner product. Okay? So now, suppose x of t is a second-order process over a subset of time parameters. So xt is second-order process, and k of xt is the covariance function of this second-order process. And t0 is an interior point of t. Then that the limit of the curve x of t as t goes to t0. Okay. This limit exists in L2 norm. Means that this limit exists in the Hilbert space of the L2 space. If and only if the covariance function, right, as x and t goes to 0 exists. So you can see this is the economic condition. Okay. The geometry, the behavior of the scalar process in the L2 space can be controlled by the behavior of the covariance function. So this is the economic condition. The most important thing is that x of t is continuous at t0 if and only the covariance function is continuous at t0, 0. When x equal to t0, t is equal to t0. Okay. So we have this result. Okay. They are economic conditions. All right. Again, I have committed properties that it's standard. Okay. So with a single argument that x of t is continuous over the whole time interval t. If and only if the covariance function is continuous over the square set. So this is the result. So continuity of x of t is corresponding to the continuity of the covariance function. Okay. A lemma t here I took this lemma from calculus. It says that suppose we have an ordinary complex value functions on this square. Okay, so f of xt has two variables, and the x and t are variables in between a and b. And if the partial derivative are continuous, so if f is partial derivative with respect to x, has partial derivative with respect to t, and has mixed double partial derivative. Right? So suppose we have that. So these three partial derivatives exist and are continuous over this square. Okay? So first order, we have two first order partial derivatives, and we have a second order, but it's mixed type partial derivative. And these three partial derivatives exist and continuous over this square. If this is true, then the mixed partial derivative can be obtained by using such a formula. Okay, so you see that this is the value at x plus h t plus k minus the value of x plus h t and this one, and then fxt. It's better to look at here in the plane. So this is xt. S plus h t plus k. Right. So this point is S plus h. Okay. This point is h. Okay. So here we have 4 points. And we take the value at these 4 points, right, and form this combination. Okay. All right, divide by hk. So this is h. The length of this segment is h. The length of this segment is k. And we let hk go to 0 directly. So it's a direct computation. Okay, it's a direct computation. And this element is equal to the partial derivative, the mixed type partial derivative. Right? So it's a lemma from calculus. Okay, so now we can apply the lemma here. That x of t is a second order process, just like here. And k of xt is the covariance function of x of t. And t0 is an interior point. Now, then we say x of t is differentiable at t0. Differential at t0. If and only if this exists. If only this exists. Because the covariance function, yeah? So we have this result. And S of t is continuously differentiable over an interval. Right? So continuous differential means that its derivatives it's also a curve, right? It's a second order process again. Right? This is second order process. And because it's differentiable means that at each point, every point in this open interval, we have derivative. And each derivative is a second order random variable. Okay, so the derivative of x of t is another second order process. Okay, another second order process. And this second order process is also continuous. Right, so x of t is continuous differentiable if its derivative function is continuous. So now x of t is continuous differentiable over an open interval t if and only if that the covariance function has partial derivative which exists and then continues over this square. So nice property about the covariance function here, right? The covariance function has partial derivative and then has mixed type double partial derivative exists and continuous over the square. This nice property implies that S of t is continuous differentiable. So from here you can see that the geometrical property of x of t depends solely on the behavior of the covariance function. Well, it's the proof I mean, it's long, but I encourage you to. So the following color actually is from the proof. Yeah, you have to see the proof. But from the proof that if S of t is continuous differentiable, second order process, right? So if S of t is continuously differentiable second order process over this open interval, then the covariance function of this second order process has continuous partial derivative. It's continuous partial derivative. And then you can see that this is the original covariance function. This is the partial derivative of the covariance function relative to x, relative to t, and this is the mixed type double partial derivative. And you'll find that they have correspondence that this is from our definition, right? Covariance function. And it turns out that this function is the covariance function of x and x. The cross covariance function, not covariance, cross covariance, because we are talking about the covariance between x and x prime. What is x prime? X prime is the derivative of the x. Okay? So it is the derivative. So this partial derivative actually is the cross covariance function of x and x prime. Here, and this one is just change the role. So it is the x prime and x. And this mixed double partial derivative is just the covariance function of the derivative process. Very interesting. So this is important result. Okay. And it was also proved in the previous proof. So this is nice formula. Okay. Very nice formula. Because you don't need to compute the covariance function of the derivative. Just take the partial derivative twice. Okay. One for x, the other for t. Right now, so it's quite general, right? Because all this just extension. Right. So the idea is that we have shown that second order process is geometry because second order process can be regarded as a curve in the Hilbert space, right? L2 space. Okay, so it's a curve in the Hilbert space. This is called second order process. And so in here, we can show that the curve is continuous or is is differentiable, right? Continuity or differentiability are geometrical property of curves. Okay, so we can use the concept to study the second order process. And we found out continuity and differentiability of a second order process can be reflected completely by its covariance function. Okay, as we have shown here. Now we go further that we have time up here. So now the rest of this section we will include more and more property about the second order process. For example, independent increments, as we have for the sum process, right? And also stationary increments, right? So these two assumptions are very important from the study of stochastic process. And so we will continue to work on that properties and to see if this property, how they affect the properties of the curve, right, in the Hilbert space. Okay? Right, so I stop here.